I just want to gauge that these surface independence thing makes more sense after 1 day's passed after I introduce. All right, here's a quick corollary of the thing. If S is oriented closed surface, I think I have a picture for that. These two are not closed surface, but really cute surface. This is not closed. Do you see the boundary of these two surfaces? There is a surface. This is actually a perfect sphere. Do you see the boundary? Boundary is up there. I've created a tiny hole up there. That's the boundary, right? So if it is coming from curl vector, this one versus if I shrink all that thing, suppose this is a balloon and there's a hole, right? And I blew it, all the air is inside, it has like this. So if I stop blowing, continue blowing, it shrink down to perfect flat, balloon like that. So the surface integral of this one versus surface integral of this tiny one is the same, right? Because the vector field you're integrating is a curl of something. That's the Stokes theorem, right? So that surface integral is equal to this surface integral of a tiny region over there. And what if I take that region even really smaller? The surface integral of all this thing is the same as surface integral of this tiny region, right? That's the Stokes theorem. What if I keep making this one small and small? And what's going to happen to the surface integral of this one is definitely the surface integral of this tiny circular by Stokes theorem, right? And vector field dot of the dr. Work done by this tiny loop around that. That's the Stokes theorem. This is equal to that, right? Well, what's going to happen to this line integral if this closed curve is becoming smaller and smaller? I think it's quite intuitive that this is going to be 0, right? Whatever that is, that work applying to that tiny loop is going to be constant, and that loop is getting smaller and smaller, and it's quite intuitive that this quantity is going to be small, right? So using this continuum idea, if I finally close up, boom, and there is no curve in there, then what's going to happen to this entire surface integral? And it's just going to be 0. Okay? All right. If the fluid density vector is this one, this whole thing measures. Now surface is, there's no opening, completely closed. Then, fluid passing through, number of particles going inside and coming outside must be, net total must be 0. Otherwise, you'll keep accumulating molecules inside or losing it. That makes no sense if it's continually flowing. It's just like a stream of water. Put that net, of sphere, the water particle coming inside, outside, is total is constant because inside that container, the number of particles remains the same. So that's the conservative. This is easier to understand. Why is this representing conservation of a number of particles in there, right? Okay, so if you take some density, some vector field, and you chose some sort of closed bound or closed surface, and do the surface integral, and got positive number, and that cannot be the fluid density vector field, right? Things like that. Make sense? So if you look at closed surfaces, and if you integrate curl of something, the surface integral, you expect the answer to be 0. Okay, so you can use that to show that, prove the given vector field is not curl of some vector field. Then you integrate sphere and realize that was 1. Then you feel, if it is curl of something, it must be 0. But I got 1. Therefore, I proved this is not curl of something. Remember, to prove that vector field is not conservative, you integrate along the circle, right? And show it is a 2 pi. If it is a conservative vector field, it's supposed to be 0, right? So that's one way to prove given vector field is not conservative. Kind of analogy in here. All right? So I think that's what I wrote down there. That's the line integral. If you go around the closed curve, you expect it's 0. It's the same phenomenon here. If you go around the closed surface, then surface integral of a curl of a vector field is supposed to be 0. All right? Nice thing to know. This was the theorem that I'm not planning to prove, but it is one of the questions that might come to you. Oh, if that's the situation in line integral, and what about this one, and stuff like that. All right, so remember that in the two-variable line integral, I think that was the case, two-variable line integral, two-variable vector field, p comma pi qj, right? There is a neat method of testing if this is a gradient vector field or not, conservative vector field, right? What was that? The cross derivative method, which was qx minus py. If that's 0, then we quickly conclude this phi is gradient vector field of something, right? Under what condition? There is some important condition. We played with this one, and that right, it has to be right. It has to be defined everywhere or simply connected region. So easy thing is that phi is defined everywhere, right? It's easier to state. It's sufficient condition to make this one happen. But the sensitive thing that you can't use this one to the vector field that has xyz in it, right? And there was one exercise that we had it before that some of you did not pay attention to the instruction and just apply this method to the three dimensional vector field, and that's not correct. So we're going to do that here. All right, so that's what we're stating in here. Suppose vector field in the space that has xyz in it, right, is defined everywhere, so that you do not have any denominators or square root inside, anything like that. If the curl, this is more complicated than this one, right? The three-dimensional vector field. If that's 0, and they're guaranteeing that that vector field you're looking at is actually the gradient vector field of something. And actually computing that gradient vector field is, again, integrating with respect to x, with respect to y, z, so it is not that difficult. But you don't have to do that. If you just have to decide whether it's a gradient vector field or not, all you have to check is this curl being 0 or not. Proof is also simple, because what is this name of this theorem? Yeah, this is a Stoke's theorem, right? If this is happening in xy, Green's theorem, right? So we actually use Green's theorem to explain this phenomena. So if it is xyz space, we have to use a Stoke's theorem. If the curl is 0, right, then you simply put the 0 in there. Then it's always 0, no matter what surface you put it in there. So that means that no matter what circular or the curve in the space you put it in there, that line integral is always 0. That was the equivalent condition of conservative vector field, and therefore is a gradient vector field. All right? What this picture is saying is that if this vector field defined in three-dimensional space is not defined in all these lines, entire this is a line described by x and y and equals 0 and z is free, right? Suppose you have a vector field that has something like this. Then that's exactly where it's not defined, right? Correct? Make sense? Then you cannot apply this Stoke's theorem. Why is that? Because if you consider this loop, you need to integrate some surface, right, that encloses this boundary. Then you have, this is one example. If you want to avoid that, you have to go around something like this. You see this surface, like a hat of a, chef, like that. But you cannot avoid that point. This infinitude of line always there is not defined, right? So this right-hand side has a problem. Correct? Yes, you can apply that. But if it is just about this one, so you have some freedom up here, then you can go around and avoid the singularity. But if this undefined is stretched to infinity, you cannot create any surface and avoid this where it's not defined, and right-hand side makes sense. It's not possible. So there is a little bit of problems occurring. But if it is defined everywhere, of course, you can just close it something called minimal surface, and then it is going to work, right? So that's where the defined everywhere kicking in. Why is this necessary? We're using Stoke's theorem. Stoke's theorem wanted to something inside what's happening in that boundary. For that one, we have to guarantee that it's defined everywhere. And here's an example. It's not defined everywhere, and we don't have this result. All right? So that's the problem we're going to do. This is the 18.2, and like I said, and in that problem, they gave you this instruction back then and asked you to use that new criteria to determine whether this is the gradient vector field or not, right? So, but many of you use the cross derivative test with x and y only, but you have to do all of them. So what is the criteria here? What do we have to check if this is gradient vector field or not? Curl. Curl of this thing being 0 if and only if this thing's gradient vector field or not. Because they are defined everywhere, right? Do you see denominator? Do you see square root? Do you see log? Because none of them are there, that we are in this situation, right? Which one do you want to try? 31? Yeah, let's try 31. That's your exercise number 2. Go determine if this vector field is a gradient vector field or not, right? You can integrate it, right? But there's an easier way, which is dealing with a curl. So we're not going to find antiderivative. Do we have to find antiderivative? No, let's not do that. Determine if it is conservative. Easier to write using this word. That's your question. 2xy, I component, x squared plus z squared, j component, y the k component. Alright, was that okay? I didn't even calculate the j component and k component because I component is supposed to be 0 in the first, and the j component must be 0, and k component must be 0, right? But I didn't get I component 0, so I stopped. Okay, it's non-zero vector. Conclusion? Not conservative, right? There's no gradient vector such that, no scalar function such that its gradient vector field is this one. It's not going to happen. Question? The same thing we do down there.